So thank you very much for the introduction. It's my pleasure to be here and welcome you to my presentation. Thanks to my previous speaker, we learned something about T-stress, so we'll connect in my presentation with that. We undertook a research project during the last 4 years actually, and I'm happy to present some results on that about the influence of multi-axial far field loadings on the fatigue crack growth behavior. So I'd like to go straight forward with a short overview of my content. I will start with a short motivation about the topic, why we did that research project. Following up, I will line out the experimental campaign, so selective experiments about that. I have some results on fatigue crack growth experiments with me, and we did further evaluations and simulations of the plasticity-induced crack closure of these experiments. So we'll also guide you through these results and end with a short summary. So as we all know, in aero engines or steam turbines or whatever, there are highly stressed components that experience multi-axial stresses. So, and these have a limited service life. So when we want to go over to a damage tolerant design, we really need to estimate the crack growth as precise as possible. So these parts experience multi-axial stresses on the one hand because of the external forces that are acting on the part. We have a centrifugal force, we have resonances, imbalances, flow separation and so on. And on the other hand, we have a complex geometric shape. So this all leads to the fact that a turbine blade is multi-axially loaded. We as a research institute, we do a lot of materials testing, but our world is somehow, well, uni-axially dominated. So when we derive a fatigue crack growth law, we do that with globally uni-axially loaded specimens, such as corner crack specimen, CT specimen, or single edge notch tension or whatever. So the question arises, how do multi-axial stresses, like we have them really in the part, influence the fatigue crack growth behavior? So, and also, when we look into assessment concepts and databases, it's all uni-axially dominated. So we worked into that and we're looking at the T-stress. We learned already that the T-stress emerges as the first non-singular term out of the Williams series expansion, and according to literature, it's capable to describe the actual crack tip constraint. So we saw in the pictures of my previous speaker that we do get an influence of the T-stress on the plastic zone. So we can imagine the T-stress acts in the crack extension direction as a certain stress and changes the size and the shape of the plastic zone. For that Griffith or biaxially loaded Griffith configuration, we can calculate the T-stress with the outer stresses here. And when we get an influence on the plastic zone, it's also plausible that the plasticity-induced crack closure that is highly affected by the plastic zone and the plastic wake is also influenced. So in industry, the Newman and McClung formula to estimate the crack closure is, well, common practice. So it uses a yield stress, the crack depth, maximum K factor, and the so-called constraint factor. The constraint factor rather refers to the actual stress state, so plane strain or plane stress state, rather than to the actual crack tip constraint that we characterize by T. So out of Newman, we get the factor U that describes the ratio between the effective stress intensity factor and the full stress intensity factor. So we were looking at these parameters with a certain investigation using cruciform specimen. So this is our, let's say, in-house geometry with 110 times 110 millimeters. We have a center of a diameter of 15 millimeter and a thickness of 1.8 millimeter. So this is very thin, and we assume here plane stress conditions. We machine an initial crack starter notch by EDM machining with an orientation of 0 and 45 degrees. And by that, or with the forces in direction A and B and the initial crack starter notch orientation, we can influence the T-stress with one specimen. So we used here a quench and tempered steel and tested this cruciform specimen in our planar biaxial test rig. It has 4 servo-hydraulic cylinders that pairwisely build the axis A and B, and in the middle there is a cruciform specimen clamped, and we attach biaxial mechanical extensometers on the specimen from the one side, and from the back side we have an optical approach where a GPU-based DIC system was developed within the project. So this DIC system allows a correlation frequency up to 850 Hz for 2 strains, and we managed it to run this system optically strain controlled. So as far as we know, this is the first biaxially system that was run optically strain controlled. So, and furthermore, we have an ACPD system to track the crack growth. As you can imagine, this test stand and the specimen allow a lot of, well, investigations on fatigue crack growth. So we were looking with constant amplitude loading on the influences of T-stress. We were looking at plasticity-induced crack closure. We were looking at influences of interspersed cycles, so overloads and underloads. And furthermore, we also carried out investigations about the crack growth direction and crack bifurcation. So today I will focus here firstly on constant amplitude loading. We carry that out under force control with an R ratio of -1, frequency of 5 Hz, and room temperature conditions. So let me guide you through the short matrix here. We use one cruciform specimen with an initial orientation of 0 degrees, with a magnitude of loading of 16 kilonewtons. We have an delta K of 25 megapascal square root meter at the crack depth of 1.5 millimeter, which we assumed as the beginning of the experiment. So we see that we get a negative T-stress of 174 megapascals here. Comparatively, we carried out a biaxially loaded experiment with a crack orientation of 45 degrees, so between the two loading axes, and we need higher forces here on both axes to meet the initial delta K of 25. So the T-stress here results to close to the 0 line. On the other hand, we were looking for the influences of interspersed cycles. So we used these reference experiments and applied an over and underload after 20 cycles. So again, we find the 22.5 kilonewton here that we used here, and after 20 cycles, we interspersed 45 kilonewton on both axes here. So what you get then is a delta K that varies between 25 and 50 when we look at that, and also T-stress is here again about 0. In this case, that is uniaxially loaded, well, we managed to get an even more negative T-stress, about -430. So important to mention, all the experiments turn out to have mode 1 fatigue crack growth. So when we look at the results on HCF loading here, we see a Paris diagram, fatigue crack growth rate versus delta K, and we have 2 fatigue crack growth laws examined by using corner crack specimen. So we can see now the difference between corner crack specimen and cruciform specimen, which is none. So there is a little bit of scatter, but this actually describes one Paris law when we refer to delta K. So we do not see an influence of the T-stress on the fatigue crack growth rate here. So we are further looking on plasticity-induced crack closure, as I said, where we applied the formula of Newman for that thin thickness of 1.8 millimeter. We assumed a plane stress condition, and Newman would tell us, well, use an alpha of 1, which is on the non-conservative side here compared to our fatigue crack growth law that we derived by corner crack specimen. So if you would use an alpha of 3 here, well, we would have the same crack closure behavior as we turned out with corner crack specimen. So we questioned that, and I will go on that topic later on. So on the HCF LCF loading, we have the same graph here, delta K and delta K HCF. We evaluated these experiments by neglecting the LCF cycles. I will not say that this is a consistent description, what we see here in terms of Paris, but the plot shows us how the crack growth rate increases by the interspersed over and underload cycle. So we see an influence here by the interspersed cycles for sure. So we were also looking how does the crack closure is affected by that overload and underload cycle. So we'll first go here on the HCF cycles. We are looking for the crack closure with three approaches. On the one hand, we have a simulation of the plasticity-induced crack closure. We evaluated data from the mechanical extensometer. And on the third place, we used our DIC system with extensive data to evaluate crack opening and closing. I will focus here in the presentation on these two topics. The other topic will be published then in the proceedings. So we have two basic models here with 0 and 45 degrees crack orientation. It is a 2D simulation of our cruciform specimen, and our approach needs a symmetry line. So if we do some thinking, we find, well, two symmetries. We apply a rigid body here, boundary conditions, and on the other hand, when we have a 45-degree orientation, we apply boundary conditions here, and we have our rigid body here to carry out the plasticity-induced crack closure simulation. So it is a 2D reduction, as I said. We use a conventional meshing approach here with an element edge length of 0.01 millimeters, and we realize crack growth by releasing the boundary conditions after 2 cycles. And then we start in Abacus a restart analysis, well, to keep the plasticity information in the element. So we also are avoiding some errors from FEM regarding locking, hourglassing, and we also use a linear kinematic hardening law here to prevent numerical inconsistencies. So this is our approach, how we simulate that, and we can have a look at the results here. What we see here is the factor U over the crack depth from the experiments. On the left side, uniaxially loaded cruciform specimen. On the right side, the biaxially loaded cruciform specimen. So triangles up indicate crack opening, triangles down indicate crack closing. The solid line represents what Newman would tell us for an alpha of 3. The dashed line indicates what Newman would tell us for an alpha of 1. So we can see from the compliance measurement that an alpha of 3, well, represents more what actually is happening with crack closure rather than the alpha of 1. In both cases, again, independent of T-stress, what we measure here. We use 2 criteria to determine the crack opening and closing in the simulation. So the first one I'm showing here is the global force balance, how we call that. So we balance the external force and the forces in the reaction forces in the ligament area, and we use a threshold then to detect crack opening and crack closing. So we see the results come quite close to what we measured, and when we look at the first node behind the crack tip, we see that we can quite a good estimate the crack closure from the experiments. And again, the simulation tells us there is no significant effect of the T-stress on the plasticity-induced crack closure here. That's fine. So we further were looking at HCF and LCF loading. So we adapted our routine here that we simulate the LCF cycle, HCF cycle, LCF cycle, and we assumed that we only have crack extension before the LCF cycle. So what we can see here is again the uniaxially loaded experiment in green, and the light green here indicates the crack closure measurement from the HCF-LCF combination. So we see an increase in the factor U because of the interspersed cycles. So our simulation here overshoots really what we measured from the experiments. Oh, I guess there's one slide missing, sorry. So when we are looking for the LCF cycle, it would look like this here. We were then looking on how does the crack closure turn out when we only simulate the LCF amplitude, just as a standalone experiment. So when we see the results here, we see that we have a good agreement between the simulation and the measurement from the HCF-LCF cycle. So we assume that the plasticity-induced crack closure is governed here by the LCF cycle, and the HCF cycle are adapting to that factor U. So I'd like to summarize shortly. We did a study on influences of multi-axial loadings. We were looking at the T-stress, also with experiments on cruciform specimen. We do not see a significant influence on T-stress, on fatigue crack growth rate, and on plasticity-induced crack closure. Independently of the specimen type, so corner crack specimen and also cruciform specimen. If there is an assessment for thin walled structure, use an alpha 3. This is less non-conservative and comes more close to the plasticity-induced crack closure that's taking place. And we see that the simulation is capable of describing the plasticity-induced crack closure within a good agreement, actually. So lastly, we'd like to thank our project partners, industry partners, and the BMWK for funding the project. And I guess I should stop now and ask any questions, and thank you for your attention.